All right, welcome to another deep dive, everybody. Today, we're going to be tackling some pretty big questions, like seriously big.
Yeah, universe level big. We're talking about space-time, energy, general relativity, all that fun stuff.
Exactly. And the reason we're diving into this is because, well, some of you have sent in some really interesting stuff that suggests there might be some missing pieces to this whole puzzle of how energy and space-time actually work.
Right, like we're talking about the fundamental building blocks of, well, reality itself, and it seems like there's some gaps in our understanding.
So let's just start with the basics, right? The source we're looking at today lays out the core concepts of general relativity. And one of the key ideas is this idea of space-time as like a four-dimensional structure, kind of like a fabric that can be warped by energy, right?
Yeah, that's a common analogy, the whole fabric of space-time thing. You know, a good way to picture it is to imagine a trampoline. Like if you put a bowling ball in the middle of it, it creates this dip, right?
Yeah, I've heard that one before.
Well, that's kind of like how a massive object like a planet or a star warps space-time around it.
Okay, I think I'm following so far. But then the source goes on to say that general relativity, as brilliant as it is incomplete. Like, it explains how gravity works on a large scale, like those planets and stars we were just talking about, but not on a super small scale, like at the level of atoms and subatomic particles. So what's the problem with applying it to, say, an atom?
Well, you see, on those really tiny scales, things get, well, weirder, like a
Yeah.
lot weirder. And the math we use for general relativity, it just doesn't quite work the same way.
So we have this theory that explains, huge chunks of the universe, but it breaks down when we zoom in on the really tiny stuff. That's kind of crazy.
Yeah, it is pretty mind-blowing when you think about it. And it raises a ton of really interesting questions. Like, for example, what is energy actually made of? Like, we can describe what it does, but its fundamental nature is still a bit of a mystery.
Right. And how does energy actually warp space-time? Like, is it pushing on it,
Yeah.
pulling it,
Right.
or is it something else entirely?
Exactly. Those are some of the big unanswered questions, like what's the mechanism behind all of this? And why does energy even warp space-time in the first place?
Yeah, those are some big questions, all right.
To really wrap our heads around all of this, we need to delve into this concept of geometrizing energy. The source mentions this, and it's a pretty important piece of the puzzle.
Okay, so break that down for me. What does it even mean to geometrize energy? Sounds kind of complicated.
It's not as complex as it might sound. Basically, general relativity uses this geometric framework to represent energy mathematically.
Okay.
We use these things called tensors, which you can think of as like mathematical containers that hold information about the shape and strength of energy and gravity at different points in spacetime. So this allows us to compare the shape of energy to the shape of spacetime itself.
Hold on. So we're describing energy in terms of shapes now. Like, energy has its own geometry.
Exactly. But here's the catch. The source argues that this geometrization, it's not complete. It works great for those large-scale phenomena, but it hasn't been successfully applied to fundamental particles like fermions.
Fermions, now remind me what those are again.
Oh, right. Fermions are those particles that make up the stuff we're all made of, like protons, neutrons, and
Oh,
electrons.
right. Gotcha. So it works for the big stuff, but not the tiny bits that make up the big stuff. That seems like kind of a major problem.
It's a bit of a head scratcher for sure, and it gets even trickier because fermions, they have these quantum properties like spin that make them behave in ways that just don't fit neatly into this geometric model.
It's like our map of the universe is missing some pretty crucial pieces.
Exactly. And that's why this whole discussion is so fascinating, because it really highlights the limits of our current understanding.
We touched on this a bit earlier, but I think it's worth circling back to. How did Einstein's view of gravity differ from Newton's?
Right. So Newton, he saw gravity as this force acting between objects, like, the Earth pulling on the moon.
Right, classic apple falling from the tree.
Exactly. But Einstein, he came along and completely reframed our understanding. He said that gravity isn't a force in the traditional sense, but rather a curvature of space-time caused by energy and mass.
So to Newton, gravity was a force, and to Einstein, it was geometry.
And that's the thing, it's this geometry, this curvature of space-time that we're struggling to apply to the quantum world.
Like, are you saying if we could figure out the geometry of, like, an electron,
Exactly.
you might be able to finally unify gravity and quantum mechanics?
That's the hope.
Wow.
That's the dream, right?
That would be huge.
I mean, we've managed to geometrize energy on a large scale, right?
Yeah.
We can talk about the energy of a star in
Hmm.
terms of how it curves space-time around it.
Right.
But the real challenge is to do that on the quantum level
Right.
with particles like fermions, the fundamental building blocks of matter.
So that kind of brings us to another big question that the text brings up, and I think this is really interesting.
Yeah.
It says general relativity. It tells us how energy warps space-time, but it doesn't really explain the mechanism.
Right. It's like knowing that the Earth revolves around the sun, but not understanding the force of gravity that causes it.
Yeah, we can observe the what,
Uh-huh.
but the how is still a mystery.
Still a mystery.
And that's where the text really gets interesting. For me, it asks these questions like, how is energy embedded in and coupled to space-time? Does energy push space-time away, or do they coexist in some more intricate way?
Yeah, those are deep questions.
They really are.
They really are. And it's like we're standing at the edge of this whole new understanding of reality.
And the text, it's like it teases us.
It does.
It says, these are clues, as we will see. What are energy and space-time really made of? How do they actually interact?
The how.
The how, not just the what, right?
Right.
And the clues seem to point to this deeper level. Here's a final thought for you all to kind of ponder on.
Okay.
What if we could describe a fundamental particle, like a fermion, purely in geometric terms?
Whoa.
What would that tell us about reality?
Uh,
What would those geometric structures look like?
what would they look like?
And what secrets of the universe
No,
might they unlock?
big questions.
Big questions. Keep those in mind and keep exploring.